okay, neurons. So this one is connected to the previous layer, so not the previous to previous block. So this will be connected to only these parts, not others. Okay, so these are connected to the previous one. So, and we have also discussed these parameters, that how many weights are required, means how many weights and what are total weights and bias. Okay, so if you are using, for example, we have discussed that 3 input, and if you have, for example, 1, 2, 3 inputs, and if you have 2 hidden layers, so 2 perceptrons in one hidden layer, and you have another final one perceptron. So in that case, you have basically how many weights are there. So it will be connected with this 3 plus 1, because here you have the bias 3 plus 1, that means it is having 4. It is also having 4, and this guy is having 2 plus 1, that is 3. So total you will have 11. So 11 weights are there. So these are called parameters. Okay, so these parameters we need to tune, and we have also discussed, needs to tune means we have to, similar to perceptron, that we start with some random values of these weights. Okay, some, for example, 0 or 1 with some numbers, and then we have to modify this weights such that we get the minimum error. Minimum error means we have a data set of 100 examples, okay, training data, and we see that out of 100 examples, how many data we can correctly classify with that specified weight. For example, if I'm saying that W is 0.45, so we'll see that with this 100 data and W is 0.45, how many data are correctly classified. Okay, and that's actually accuracy. If I change it to 0.52, then what is the accuracy? So if my accuracy is maximum, then I will consider that weight as the best combination. Okay, so whatever, if I'm having W1 to, for example, if I'm having 11 weights, W1 to W11, okay, so I have to set all these values, okay, and these values, there will be different combinations. There will be different combinations. W1 can be different, W2 can be different. So I have to find out a combination of this, all these W's, such a way that out of 100 examples, how many I'm correctly classifying. Okay, that means my error is minimum. Okay, my error is minimum. Yeah. Yeah. So then we have seen also this different activation functions. So in perceptron, because at the end we are doing this simple greater than this line is thresholds or not. Okay, so that's why it was like greater than thresholds or less than threshold. So it was step functions. And in multi-layer perceptrons, what we'll be using, that because we'll have so many weights are there, and these are connected one after another, and at the end we will be using this error. Okay, so how many samples we are correctly classifying or not correctly classifying. So accordingly, all these weights will be adjusted. So these weight adjustments will be done with a backward propagation that we have discussed. But when we'll be doing this backward propagation, there we require one this what you call this gradient descent. Okay, so we have to make some partial derivative. So some mathematics are there. So actually it is easy to adjust these weights according to this formula. So when we are using this derivative, partial derivative of this weight, partial derivative of this loss error, okay, with respect to weights. So there we need this, we cannot use these step functions. We require some other activation functions. So that's what we discussed about this sigmoid. We have used, we have discussed tanh, ReLU, and this leaky ReLU. So these active functions are we can do it derivative, okay, easily. And there are also some good things of these activation functions. that the calculation is very fast, okay, or for those functions. You can also use some other activation functions if you want. Okay, so if someone wants that I want to develop another new activation functions for my problem, it is possible, of course. These are not just only a set of functions. You can also come up with a new activation functions, and you see that whether this activation function is giving better results or not. Means giving better results means because we have so many weights and we want to find the combination faster. So we will start from random value, some zeros, okay, or one something, and we want to find the best combination faster. So that we have to do using some good activation functions. So that's why there are different experiments, research going on that which activation function is good. And then we are going to see that how this learning algorithms are used. Okay, so this is back propagation and gradient descent that we just skipped. We could not discuss yesterday, and then we are going to discuss these 2 points, back propagation and gradient descent. And after that, we are going to see this regularizations and optimization, how we can tune this multi-layer perceptron so that we can get the solution faster. Okay, so that's the refreshing the previous concepts and the agenda of today's lecture. Okay. Now let us move. We have discussed these activation functions, multi-layer perceptrons. Also, we discussed that we have if we have this inputs, and then we have different layers, and then we these are the hidden layer 1, hidden layer 2, and then we have this final perceptron that's actually giving the results. And if this part is not there, we know it is just a simple. If it is only this part, then I can know that how to train it. But as there are so many things, so how I will adjust for each of these weights. Okay, so that's actually the problem. So how we can do it? So this is actually done using this forward step. So forward step, this is simple. So we first set up this architecture, like you have 3 inputs, and for example 2 layers or 3 layers, whatever architecture you have, and then you said that okay, how many perceptrons are required in the first layers or second layer. And then you also need to say that what is the activation, whether you are going to use the sigmoid or 10H or ReLU, and then that's it. So if these are done, then given any input x1, x2, x3, so this forward step, forward pass, what it does, you just for this guy, so it will be doing w1 x1. So for this guy, it will be doing w1 x1 plus w2 x2 plus w3 x3 plus b1. Okay, so b1 I can write w0 x0 that you have seen. Okay, and then this is the summations, and then after that I am using is sigmoid functions. Okay, so sigmoid functions, whatever sum it will give, and this sigmoid functions will provide the output from 0 to 1 range. Okay, that we have seen the sigmoid functions output. So whatever sum you have, this sigmoid functions will provide the values from 0 to 1. So from 0 to 1, right? And then everywhere, similarly, you have all these different perceptrons. Everywhere you are getting 0 to 1, 0 to 1, 0 to 1, something. And then you have this next perceptron. Okay, so this perceptron will also take similar thing. So you have some, you consider that these are the input and these are some weights, and then you make some addition, summations. Okay, so for example, w1 x1, here you have this x1 and w1. Okay, so different w's, and then you have also this this activation function, sigmoid or 10H, whatever, and then you get another output that is 0 to 1. Okay, and then at the end you can also use here sigmoid functions. Okay, 0 to 1, and then you can get the results. So results, it will be provided that okay, so if you are using here, we will not be using this step functions. Here we will also be using some, for example, sigmoid functions or tanh function. So the output will be probability of the value of 0 to 1. Okay, so range will be from 0 to 1. So it will say that whether it is close to 1 or it is 0. Means if it is if you are getting 0.8, that means the class level is close to 1, you can say. Okay, so that's actually how this is the forward step. So when we say that 0.8 I am getting, that means there is some error, 0.2. So this error I need to adjust. Okay, so it will be for a single example. Okay, if I am having an example with I1. So if I am having an example of 100 examples, so I'll for each examples I will get the error, and then I have to adjust all these errors. So these adjustments will be done in the backward. So whatever error I will have, these errors will be first contribute in this modification of these W's. Okay, and so I'll be modifying here. This W's in the last layers will be modified, and then I'll be modifying here. Okay, in this part, and then this part. So this is called backward step. So you have this, we'll get the error, and then we'll make the backward step, and then these errors will be adjusted. So I didn't discuss about this error surface, so let me clarify it again. I think I discussed a little, but not in a detail. So when this error surface or loss functions, when I say, so let us consider that we have only a single weight, okay, W1 or W2, any W values, okay, any W. So W value can be, for example, 0 to 1, okay, whatever. And then you have this error. Error means if your W is value is 0, then you may be having a lots of error. Maybe error is 100%, let us consider. And then if you change it, the value of error to this W to 0.2, then maybe error will be something like this. Okay. And then if you change this W to 0.2, and then you get some error, less error. And then after that, if you modify, then you are getting something a little more. Okay, it goes up. And then if you change it again, okay, means you are trying with these different ways. I'm just not saying that you are changing it. I'm saying that if you try with these different values of weights, then this is the error surface, and we see that 0.0 you will have lots of error, 100, and this is 0. And you see that at 0.5 maybe your error is very less. It may be error is 10%. Okay, and this is 0, it is maximum, and after that the error is going up. Okay, so here you see this error surface. This is the error curve. Okay, so it means for each weight, you can plot it in a one-dimensional way, or if you have this W1, W2, W3, if I see plot it in this way, W2, W3, then it's actually a four-dimensional curve. Okay, you will see like a mountain. Okay, if it's in a two-dimension, it will be a mountain. In three-dimension, four-dimension, you will see that it's actually a error surface. Okay, it's a surface where you will have different minima. Okay, so and some local minima, some global minima. Global minimum is in which value you are getting the minimum least error. Okay, and in some value you are getting the error. Means what I'm saying that if you are going down, and at some points you got less error, and then after that you see that if you move in the right side or left side, this error is not decreasing. Error is always increasing. Okay, so here if you are here, and then if you go up, or if you go to this left side, or if you go to this right side, always this error is actually increasing. So that means this is a minima as well. But from this minima, you cannot go to this higher to the next global minima, because there is a peak. Okay, starting from here. So using this gradient descent algorithm, so you may be stuck here. So this is called a local minima. So this surface looks like this kind of curves. Okay, so where there will be some minimum point, and somewhere you you can get stuck. It's a local, and somewhere you are actually having this list minima, that is global minima. So what we want the W value, okay, in which we get the minimum point. Okay, so we have, this is the curve. Okay, this is the equation of this error surface with respect to this W1. Okay, and now if we want to find the minimum error, okay, with respect to this W, then what we have to do? We have to find out this first order derivative. Okay, first order derivative, that means del E by del W. Okay, and then we have to see that where it is 0. So this in which point this point is 0, that means this is the minimum. Okay. So these are the minima point where this derivative, this gradient del E del W, it is 0. Okay, so this with respect to this W weight, this points, there is, this is the derivative is 0. Okay, that means this is minima. Okay, so this we want. So if we want to know, we want to get the error. Okay, this is the error, and we want to find out in which points, in which value of W we get this minimum. This is very interesting. This we want. Okay, we want to have the minimum error, right? So we want to know these points only. Okay, so in which points we want to, on which value of W we get the minimum error, right? That we want. So we have to make this del E del W. So if we can get this using this equation, and then we will know that what is the value will be coming for W, and that's my W value. Okay, so that is the weight. Okay, so I have the error, okay, which is dependent on this W1, W2, W3, all this W11. Okay, and then what I am doing, I have to make a partial derivative with this, each of this W, and I have to check that, okay, where I am getting the derivative as 0. Wherever I get the derivative 0, that point is the minimum. So that we have to find out. So now let us calculate, now let us do this, how we can find out this, the value or combination of these W's, where we get the minimum error. Okay, so what is the error? So let us see that we talked about this error. So this is the error, for example, and then if you see that what is the error? So error will be in the perceptron, what we have seen, error is just D minus Y. Okay, that means 1 or 0. D is ground truth and Y is you are predicting. Okay, it will be Y is always 1 or 0. Here ground truth was 1 or 0 in the perceptron we have seen. Here what I am doing, because we will be using this we are not using the step function, so Y will be always either with some number 0 to 0.2, 0.3 something. Okay, so there will be some errors. So there will be some fraction of errors, that it is 0.8 or 0.6 if I'm just making this subtraction. If it is the 1, if I'm getting 1, that means there is no error. Okay, and if it is 0 and I'm also getting 0, there is no error. If it is 0 and I am getting 0.2, that means the error is 0.2. So what I need to do, so the error I am calculating that for each example, the error is whatever is the ground truth minus what I am predicting. Okay, and then I make a square of this difference. Okay, so the ground truth is 0 and I am predicting 0.2. That means the difference will be 0 minus 0.2. And I'm finding out that square terms. Okay, there you see this square term is there. So why this square term? Because sometimes it can be positive, sometimes it can be negative. Okay, so if it is 1, if it is 0.2, sometimes it is positive, and if it is 0, it is 0.5, then it will be negative. So to avoid nullifying each others, so what we want, we are using this square term. Okay, so square term will help you to add all the errors. So for the first examples, I1, I am getting error like 0.2 square, and second examples I am getting error 0.3 square. Okay, so I am adding all these terms. Okay, so for 100 examples, what is the error? And then what I'm doing, I'm having a 1 by 2. Okay, so 1 by 2, I have added one. Actually, it is 1 by 2n. Okay, so because if it's an average, if I'm having this, it's a single error. Okay, for one example, R example, this is the error. For if you are having n examples, then you have to divide this total by n. And then why this half 1 by 2 terms comes? 1 by 2 term comes because of this mathematical facility. Okay, so we'll be doing some derivative. So to cancelling some terms, so this 2 is coming. But see, if whatever error is there, if half is there or 1/4 is there, it doesn't matter. Just to make the mathematics calculation easy, so I'm just adding this half term. Okay, so I'm considering this error as 1 by 2 of summation of dr minus yr whole square. Okay, this is the mean square error. And then if I'm having, it is for single example, R. Okay, R is for R example. If I am having 100 examples, I'll be doing for each of these examples and dividing by 100. That's actually comes as a mean squared error. That means whatever is the error, this is the error, then square term, and then I am doing a 1 by n. Okay, so that's actually your mean square error. And now let us see that how this back propagation works. Okay, so I will first explain you how we can do it, this back propagation, and later I will explain the mathematics also. Mathematics is not so intensive, but I will explain. But if you some of you want to avoid, you may avoid. But for the sake of completions, I will cover that mathematics as well. So you have now let us consider this example. We have this input. Okay, so input, you have this 3 examples, and you have one hidden layer. Okay, so now let us consider one hidden layer. There are some perceptrons, and you have in the output layer also some outputs are coming. So for example, it will say that it is 0 plus or not. It will say 1 plus or not. It will 2 or not. And this layer is termed as J. Okay, so that means it will be, I can say that it is whatever input is there, this layer I will term as J. Here, this I will be calling as ith layer. Okay, and this one I'm telling as kth layer. So this weights from this hidden to output will be WIK. So you can have WIK1, WIK2, all this. Okay, and similarly you will have this from J to I. You will have WJI1, WJI2, all this. So for this back propagation, so for this full training, what we have to do? So first we have to set that, okay, so how many number of neurons are required. So this is actually up to you. Okay, so it is a hyperparameter, so you have to test with this different numbers, different combinations. So you can test with this 4 neurons or 5 neurons or 2 layers, whatever. And then we start with some initial weights, okay, random values. So all this WJI and WIK all will be set with this random values initial. And then we have to set with also some activation functions. Let us consider a simple one, that is sigmoid. Okay, so here also we have sigmoid, here also we have sigmoid. So means we make the summations that I have explained here. Okay, and then we are using this sigmoid. Okay, so and then we get the output. So first, what we have to do, we have to make the forward pass. That I said that I have this input for one examples. I propagate this information from input to hidden layers, and then the output, whatever I have, I can calculate the summation sigmoid functions. I can get the results, and that results will be multiplied with this weights, and I will get the summations here and find out that what is the output. Okay, so what is the value of y? So propagate information from hidden layer to output. Next, what I'll be doing, I'll be calculating the error. So error is, what is the error? So if I'm predicting like 0.2 or 0.3, that means what is the error? So error will be y minus actual. Okay, so whatever I am predicting. So whatever is the ground truth, that is 1, and I am predicting 0.2. So that means the error will be 0.8. So I will calculate this error and for each of this output, and that error will be propagated to this first. In this, from output to hidden, means these weights will be adjusted first. Okay, so this adjust weights in between hidden layer and output layers. Okay, these weights will be adjusted, and later this weights will be adjusted. And this process, so I am adjusting this W's, and then similar to your perceptrons, this process will be repeated. Okay, multiple iterations. So then again I will be doing this forward pass and backward pass, forward pass and backward pass. So it will be go to step 4, means I am doing this forward pass, backward pass, and then until you do not have this minimum error. Okay, so this process will be going on. That's the back propagations. Now, if I'm going to this mathematics, okay, and that how we are deriving that what is the value of this W's. Okay, so what that, for example, we have seen in this perceptron that what is the value of this W, how it was adjusted. Like if you remember, W was adjusted W plus eta into d minus y into xi. Okay, x. So if you remember in the perceptron, so similarly here also for each W's, what is the adjustment, how we can do this. Okay, so here we have already seen this error for one sample, it is 1/2 of this errors, mean squared error. Now how we have to find out the update rule for wgi and wik. That means if I am having the 11 weights total, if I can have 110 weights or 2000 weights, whatever. So each weights, okay, so I need to adjust. So W1 I need to adjust, W2 I need to adjust. Okay, all these W's I have to adjust. So what is the formula? So similar to perceptrons, I'll be doing whatever the new value will be the old value of the W minus eta into del j, that is the partial derivative with respect to this error. Okay, so that we have seen this error surface. You have this error surface, if you remember, something like this. Okay, this is the error surface with respect to W. Now we want to find the del Wj. That means we need to find the derivative. So that's actually the gradient descents. Okay, so I am coming to this part. So it will make this derivative, and with which combination of W it will give me the minimum value. That's actually we are doing it, and that part will be done using this gradient descent. So in simple way, so the formula is, we see just a minute. Yeah, here you have we have this each W's will be modified. Okay, so W is modified with this previous value, with eta is the scaling factor and this derivative. Okay, so now what is this value? Delta of eta, this eta delta of E is the error, and by partial derivative of 1, 2, 3, 1. Now we have to do it. We have to do these calculations. Now let us do it. So first we have to solve that del E by del W. So remember that when I will be calculating this derivative, okay, this W's, so when we are calculating this updations rules, okay, so here I have said first whatever error we will have, first I will be adjusting this WIK. Okay, this is the first layer, WIK1, WIK2, all this, and then once this part is done, then I will be going for this WGA. Okay, this next layer wise. Okay, first I will be going for this from the backwards. Okay, whatever error is there, I'll be adjusting this wik, then I'll be going for this wgi. So this is the process I'll be following. So wik, if I want to modify, okay, del e by del wik, so we have to know that if I want to calculate this value of this delta e by delta wik, so how we can do it? So we have to find out the dependency, how this error is related with this wik. Means you have this error, you have this, these are the errors we want to, these are the weights we want to adjust, okay? And now I have to know that what is the adjustments we have to do, okay? So how this error, if we want to go for this partial derivative with respect to this error, that means we have to know how this error is dependent on this wik. This is wik, how it is dependent. So note that wik and e, how these are related. So this is related. E is, if you see, E is basically, we have already seen error is this one, dk minus yk whole square. And then y is, if you see this is error is equal to half of summation of dk minus yk whole square, okay? And then dk is known, okay? Error is, then yk, how yk is dependent on wik. So yk, how yk, what is yk? What yk will be sigma of summation of this wxi, okay? Wik into xi, okay, right? Yk, whatever I am getting here, y is sigma of wik xi. Now you see that e I am getting with respect to this wik. So this is the dependency. So now I am using, if we know this dependency, so I'll be using this chain rule. So chain rule, if we just do, it is very simple, very easy, okay? So you see this now, del E, del wik I am finding. So first I am finding this wik, it's a chain rule, E del yk, and then yk, I have used yk by sum by wik. Now these are the three parts, delta E by delta yk. So what is this? So if I have to calculate these three sub parts, okay, delta E by delta yk by delta sk by delta wik. Delta ek by yk is very easy. You know this E as half of dk minus yk square. So if we do this delta with respect to this yk, okay, if you do the derivative with respect to yk, then what will happen? Two terms is cancelling each other. So you see half it was there and 2 is cancelling, 2 into dk minus yk into minus y. So that comes as minus dk into yk. So that's why I said that half term was there, okay, because we are going to cancel these two terms, okay, 2 into half. So now it is coming as this part is minus dk into yk. And del yk by del sk, what is that value? So yk is nothing but the sigmoid functions, this is the activation functions of this sigma, because we are using this activation functions, okay, that is the sigmoid and this is the sum, okay. So this can be tan h or anything. So this is, I'm saying it's a g. So del yk by del sk will be g prime sk. So g prime sk, if you see this derivative of this sigmoid, there is actually a very simple formula. If you make this partial derivative of the sigmoid, it comes as a yk into 1 minus sk. Okay, it is very simple. That I think I have this value. Okay, so just, okay, I'll show you, okay, later. And then you have this remaining part is sk by wyk. So sk is wyk xi. This is the sum. You know that sum is just all the whatever weights I am having and then xi. If I just multiply, this is the sum. So if I am just making this derivative, okay, with respect to wyk, this will come as xi. So now this term is coming with whatever parts we have. If I just take these parts one after another, and it comes as a very simple way. So now adjusting weights is actually simple. So this you see this wik is whatever old value plus eta. Eta is the scaling factor, and delta k is just dk minus yk into 1 minus yk. Yk is the whatever you are predicting. Okay, dk is the actual value, ground truth. Okay, so this term is known, and xi is the this part. Okay, so whatever is the output here, xi is the this part output. Okay, so you know this, how we can adjust this wik. So all these values will be adjusted. So whatever old value I have plus eta scaling factor into this number into xi. Similarly, I can do it for the wji. So wji, how it is dependent on this error. So I have to find out using this chaining. Okay, so you see that it is also simple. So what I am doing, E by yk, yk by sk by xi. Okay, so I am just finding from this last term. Okay, see this, it is E error, and this error is dependent on this y. Okay, because after activation functions we are okay, yk is basically if you just subtract, then you will get the error. And yk to sk, it is the activation functions. After applying the activation functions from sk, you will get this y. Sk to xi, you will get by summation of this xi into wik. Here you are actually using this wik, and then you have sk and del xi del si. Okay, here you see this sk and it is si. Okay, that's actually a trick. Okay, so that I'm going to show you also. No, here you have this xi and it's xi. Okay, so xi delta xi, you have xi by si. So xi and si. So xi, it is the outcome. Xi is nothing but this outcome of this part, that is y. Okay, and it is the sum, and s by wij. So if I just do this calculation, okay, so this will be, so I'm just quickly finishing. Okay. So delta ek we have already seen, dk y sk we have seen, and sk by xi, it is this part, and then xi by si. Okay, so this comes as this part, yi into 1 minus I, and del s by del wij, it comes as this one. Okay, simple. So at the end, this formula is actually coming with a very simple way. This is delta wij, these parts, all these parts are coming, wgi, this old value plus eta into del k into wik, yi, 1 minus yi into xi. Okay, so what is that? So let me show you again. So these are the update rules. Okay, so if you just if you could not follow, it's okay, no issue, no problem. Okay, just to sake of completion, I complete. Okay, this mathematical parts. If you do not understand, it's okay, no issue. I will share the slides, you can go follow through. But at the end, what I have received, these are the two things. These are important. I needed to update wgi and wik. Okay, wgi this part and wik. So wik is adjusted using this formula, old value of wik plus eta into del k into xi. Okay, so where del k is dk minus yk. So whatever I am getting this yk, and this is the subtractions of this actual value into yk into 1 minus yk. And wji, this part, it is, you see here, this old value of this wgi plus eta into del k. So whatever it was there previous, that's coming, and then wik. Okay, so wik, the same value is coming again. So whatever I am updating, that part is coming into yi into 1 minus yi into xi. So you see that whatever for this delta wgi modifications, I require this wik. So I have to adjust first this one, then second this part. Okay, so that's why it is this backward direction. First I am finding this error, then I am calculating this wik, then with that value I am modifying this wgi. So at the end, this updations rules are very simple. Wik, this all these weights, how will you adjust, and wgi, how will you adjust? Okay, using these two formula, basic simple formulas. That's it. So if you see this surface of these errors with these different w's, okay, so this will be like a mountain, okay, in a 3 dimension, and let's consider that you will have actually, maybe it can be of 2000 weights. Okay, so w 2000 dimension. You have, if you are going for CNN, okay, you will have basically 10 to the power 6 the weights. So many weights are there. And then you start with some values at randomly. So for example, you pick up some values of W's. So it can be 0W1 as 0.7 and W2 as, for example, 0.4. And then you modify these W's using the formula. So we are doing this partial derivative. So that means it's actually going down slowly. Okay, in this surface, okay, goes a little lower, and then it goes something like this. Okay, so at the end, so it will find out the path. Okay, so it will go down slowly and reach to the minimum error. Okay, so that's the gradient descent algorithm through which you actually get the minimum of this error. There is another thing I needed to tell you. You see here that I am using this multiplications Wji, okay, which is multiplied with this Wij. And there are several y terms and this xi terms, eta terms, okay. And if I am having, for example, 3 layers, okay, so if I am having this ik, ji, there is another layer, then that will be modified. For example, if I am having another layer like G to J, then it will be updated Wgj plus eta into some part, okay, and then you will have this Wgj. Okay, so that means those parameters, those weights are all coming here, and then you will have this Wik. Okay, all these are coming here. So what is happening, then if you have 3 layers, you see that you are multiplying 2 times, 3 times, okay, the same, this is different weights. And these W's values will be, for example, 0 to 1, means it can be 0.4 or 0.02. And then if you multiply these decimal numbers, okay, several times, for example, if you have in CNN, convolutional neural network, okay, 100 layers. 100 layers means layer 1. There you have only 2 layers, layer 1 and layer 2. In CNN or RNN, you will have 100 layers or more. So you will be multiplying these numbers again and again. And so these numbers will be very small, 0.00003. Okay, so or sometimes it will be 0.0000001. So these are actually going very slow, and at the end, these actually do not provide any information. So that's called this vanishing effect, okay, vanishing gradient. So you are multiplying the small numbers again and again, okay. So at the end, you actually, when you want to update, so this at the beginning, contribution is actually very low, okay. So those weights are actually not providing any details. So this you are adjusting with very small values with some numbers. Okay, so that's actually, these are not contributing anything. So that's the vanishing gradient problem. So now let us consider this XOR problem. Okay, so if we have this XOR, and in this XOR we have this J, I, and K. We have these different weights. W11, W21, 12, 22. You have this bias W10, W20. You have this another W31, W32, W30, and this is the Y. So if I want to start with something and then I need to find out the solution model, so I have all these W's, okay, how many weights? 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1, 2, 3, 4, all these 9 weights I need to adjust. So I set up or start with this random values of all these W's. And see with this forward pass what is my error. Okay, so I just calculate the error. How will you calculate? Because I know, for example, I am having this 4 examples training data. Okay, so training data 0, 0, I am getting 0, 0, 1, it will be 1, 1, 0, 1, 1, 1, 0. So if I am having this different combinations of these W's, so for this first example, my prediction is, for example, 0.51. Okay, so with this forward pass, if you just multiply with the 0 and 0, okay, you see these calculations with this sigmoid functions. Okay, this is the activation function, and this eta is 0.5. With the same formula, whatever I have used, if you calculate, the predictions is 0.51, whereas the actual value is 0. That means error is minus 0.51. So for these 4 values, you will have these 4 different errors. So from these errors, you adjust now with this, all these different weights. If you just calculate these 4 errors, okay, make the average, and from this all these 4 errors, and then if you adjust all these weights that according to this formula, first I'll be adjusting. What are the weights? I'll be adjusting 30, 31, and 32, and then I'll be adjusting this 10, 11, 12, 21, 22, 20. Okay, so you see that how we are adjusting these values. So this all these weights are modified accordingly. Okay. So this will be the some equations of lines. Okay, so if you see, for example, this perceptron. Okay, so you have this one, and this guy, I do not remember which one is for what. So this may be for this equation. If you see this, because one perceptron and you have this this 2 input and 1 bias, so you can find out the equation of light that's actually coming here. And for this guy, this is this comes as, I think, this one, and this one is coming with these solutions. Okay, so finally at the end, it's coming with this or this combination of these 3 perceptrons. Okay, combination of this one is coming with this 2, 1, and 2. Yes, and it gives the answer. So if I see this epochs, okay, epochs means for one, if you just run for all these 4 samples, okay, and this is one epoch. Means for 4 examples, I'm calculating the error, and then I adjust. Next I go to this second pass, okay, for all this training data again. Okay, that's means once I complete all the training data, that's one epoch. So initially this error, here you have this error. Okay, and this is the epoch. Means first, for example, initially my error is huge, and slowly my error is actually going down with the increasing the number of epochs. And at some points you see that there is less error. Okay, so you see that there is no error after some time. So one question here, if you have noted that why in my calculations I have done this minimum, okay, so why this term is coming as this Wj minus this formula. Okay, why this negative term comes? So let me discuss this point a little further. Okay, so what I am doing, so each weights will be adjusted according to this partial derivative formula for each weights. Okay, so now let us consider one simple one single weights only, W1. Okay, and this is the error. So let us consider that for some values W1 as A, for some value. Okay, so I am getting the error, this part. So here in these points, what will be the derivative? Okay, so derivative will be del W1, that is less than 0. But this derivative is negative. Okay, and if I have this negative, okay, then what we want to do, I want to modify the W, okay, I want to go to this part. Okay, so I need to change this if this derivative is negative, I want to go to this opposite side. Okay, if I am having some W with this B, okay, so for example at some points my W is here, B value, and my gradient, okay, gradient is here, okay, it is positive. So in that case, what I will be doing, I want to reduce, because I want to reach here. Okay, so I want to go to this opposite side. So it will be, we need a decrement of this W. Okay, so that's why when I am having a more value, I want to decrease. When I am having a large value, when I am a negative value, I want to increase. Okay, the W. So these two, so when I am having this W very small, means when the gradient is negative, I want to increase the W. When my gradient is positive, I want to decrease the value. So in both cases, what I'm doing, I'm actually moving opposite to the derivative, okay, to reach to the minimum. Okay, so that's why whatever derivative I'm getting, okay, so that's I'm doing this opposite, means minus. Okay, so whatever, so if it is positive, so I'll be doing it, I'll be reducing the W value. If it is negative, I'll be adding the W values. Okay, so that's actually means whatever derivative I'm getting, so I'll be changing this sign. Okay, that's why Wj minus eta into this partial derivative. So this multilayer perceptron, how it, you have usually it approximates all different non-continuous functions also for with two hidden layers. Okay, so two hidden layers means you have for example input data, and you have this first hidden layer 1, you have second hidden layer 2. With two hidden layers, most of the complex problems are approximately solved. So if you have a single layer, that you have seen already, this perceptron can only solve using a linear separator. If there are two layers, okay, so two layers like for example one hidden layer, and this is the output. Okay, one hidden layer. So there we can solve this XOR kind of problems. Okay, where you have this data in these two different regions. If you have these two layers of hidden layers, then you can solve these kinds of data. So for example, you have plus data, and these others are negative data. So you can solve something like this as well. Okay, so this with two hidden layers, it is possible to solve any non-continuous functions. Okay, so I can take some of your questions, and then I will go to this overfitting and this regularization explanations. Yes, any questions you have?
Thank you, Dr. Pathak. Purnima, can you please unmute people who want to ask questions, or you may ask questions through chat also.
Yes,
yes, thank you.
Yes, so as I was saying, this sigmoid function is easy. So you'll see that sigma function is this one. If you make the sigma derivative of the sigma x, it will, you just check, okay, it will come as this function. Okay, that's what we have done. This we have this sigmoid functions, the g prime. Okay, g prime when we are doing that is coming as y into 1 minus yk. So according to this formula. Okay, yes. If you have any questions.
So sir, first.
Sir, good evening, sir.
Good evening, madam.
Sir, each epoch is an iteration.
Sorry?
Each epoch is treated as an iteration, sir. Iteration.
Okay. Iteration. Yes.
Yeah.
Epoch is, for example, you have this, you have a training data, and then you have, for example, 1000 examples. Okay. So 1000 examples, if you are doing for all these 1000 examples one time completely, that's one epoch. Okay, so sometimes you can say that epoch and iterations both are same here. Means iterations is actually epoch is epoch is here. One epoch means you are covering all these 1000 examples. And iterations is how many epochs you are doing. Okay, so you can have, for example, 100 iterations. After 100 iterations, maybe the error is actually going down. But for one step, for one iterations, you have to cover all these 1000 training examples. That's actually one epoch. Means when you check all this for each of this training data, you find out the error and then you modify. Okay, so that's one epoch. And then if you want to complete, for example, 5 epochs, that's actually for example, you can say that okay, 100 iterations of 5 epochs or 10 epochs. Okay, so in that way, it is epochs and iterations are same. Yes, any other? How to decide exact number of epochs? Okay, so that we are going to discuss. Okay, in later. So it is up to you. So first you will be checking this this curves of the training data and testing data. Okay, training for the training error you have in a data sets. Okay, you have a data sets, and then some part is training. Okay, and some part is validations. Okay, validations. So what we are doing? So we will be training our parameters. Okay, in this training more examples, all these examples, and we'll see that how this error is changing. Okay, so how it's actually coming down, and then we'll also test in the validation data sets. Okay, so that we are going to cover. Okay, later after when I start the next sessions, next this regularization optimization, there will be covering. So you will see that at some points this error is going up. Okay, so there will stop. Okay, up to this many iterations or epochs we will continue when we have this minimum error.
Dr. Partha, one question regarding use of possible use of GA instead of SGD, considering that it is a better global optimization methodology. Is there a scope for that?
Yes, we are going to discuss them. Okay, in this next sessions, this how we can, what are the different optimization approaches, their gradient descent, stochastic gradient, all we are going to discuss next.
Okay, thank you.
This is a basic pipeline. Okay, whatever we have discussed now, this is a first perceptron and then multi-layer perceptrons. This is a basic pipeline, and now we are going to see how we can tune these different parameters such that we can actually reach to the minimum error faster way. Yes, any other questions?
Yeah, there are.
Shall I continue? Fine.
Yeah, there are 3 more hands up. So let me. Ganraj, can you?
Yes, sir. Am I audible?
Yes, yes.
Yes. Good evening, sir.
Yes.
Sir, my problem is with a physical design. So I'm going with an RF design. So in that, we'll be considering some parameters. So those parameters, what we are getting the output. So there is limited number of inputs over there. So let's say around 24 sets I have done over there. So
24 features, right?
Yes, sir.
Okay.
So whether I'll be able to not 24 features, 24 input sets, like in the total number of outputs what I'm getting is 24 over there.
My output is 24.
Output is two outputs are there, and
outputs are 2 outputs. Okay.
2 outputs are there.
Means either yes or no.
Yes, it's not S11 parameters and S21 parameters are there. So that S11 and S21 parameters. So for that I'm considering a particular structure over there. I'm having some 24 variables or 24 sets over there. So whether that would be sufficient for iterations that we can consider, so that we'll be able to get the efficiency over there. We are having
you are saying this 24 features, right? 20 means X1, X2 up to 24.
No,
right?
X1, X2. So I'm having just 4 features, sir.
Okay,
4 features are there.
You are having 4 features, right?
4 input features, and yes, sir. And I'm having 24 sets I've done like this, because for different, it's a small variation I've done. And
okay, so that's different. Okay, so you can have changed something features. Okay, so at the end you are having 4 features, and then output
yes,
is
sir.
1 output,
and
right?
Output I'm having just 2 parameters, S11 and S21 parameters. That is 2 features I'm having. So what
Two
type
features or
of
two output?
two outputs I'm having, sir.
Okay, S11 and S12.
S21 parameter. So just two outputs. And I'm having the number of sets what I can consider over here is whatever the X1. I'm having 24 variations I can consider.
Fine.
And,
yeah.
And so whether that would be sufficient or still I need to go for much more readings over there. Means if just with the 24 readings.
For 24 readings means from this X1, X2, X3, means different examples,
So
right?
he is perhaps thinking about 24 samples. Am I
yes,
right?
sir. 24 samples. 24
yes,
samples.
24 examples. Yeah, that's understood now. Okay, I1, I2 up to I24. 24 different examples. Okay, and then
yes,
you have these features X1, X2, X3, X4, these four features,
sir,
right?
Yes, sir. Yes, sir.
And this is
sir.
the output. You have S11 and S12 output, right?
Yes, sir. Yes, sir. So,
okay, so 24 samples are very less. Okay, but still you will get some results. Of course, this will provide you some results. You see, using this XOR, we have only 4 data.
Yes, sir.
Okay, we have only 4 data. That's
yes,
we
sir.
have got the results. Okay, so using that also you will get surely you will get some results. But if you have more data, your results will be better.
Because when we are going with the physical parameters, so we will not be able to go with these many variations over there. So
fine. Yes, you will get. So what you will be doing? So you have these features X1, X2, X3, X4. Okay. So you have these different examples, 24 different examples. So and then you design with this number of layers. Either you can do it a single perceptron. You can also do it single perceptron. Otherwise, you can make it with a one hidden layer. Maybe you can design how many nodes you require in this first hidden layer and second hidden layer, and you see that okay, so you have to try with this different you will learn, I think, in this hands-on, and then you will see that with this what are the different architecture based on which you will get the maximum results.
Okay, so this is means I'm thinking of an optimization of a particular physical design, what RF design that I'm having. So for that time,
no, you will get whatever you are expecting. This S1 and S2. Okay, with this 24 examples.
Yes.
If you design these architectures, okay.
Yes, sir.
Okay, so you will get the results. Whatever you are saying in this, according to the training data, you will get.
Okay, sir.
So you just check with this in the hands-on. Okay, and I think in hands-on you will be provided this architecture with this Python or with the sklearn, and there you will just need to provide this architecture, that how many nodes in first hidden layer, how many nodes in second hidden layer, and what is the activation functions, and that's it. You will get the results.
Okay, sir.
Yes.
Thank you, sir.
Yes, thank you, sir. Okay. Any others?
Yes, sir.
Hello.
Yes, madam.
Good noon, sir. Sir, for multi-level classification, I want to design weight matrix as compared to using the transfer learning weight like modular train on ImageNet and Coconut. Like I'm applying on VCC 16, but my results are not up to date, and so I want to design weight matrix for my application. So how I design it?
Okay, so you want to initialize these weights, right?
Yes, sir.
Okay, so there are several functions. Okay, this in the Python library, sklearn libraries, there are actually, once you start this running this code of these multi-layer perceptrons, you will see that there are some functions which will provide these initial values of weights. So you do not need to start with randomly. Okay. So I do not remember exactly what are the functions. So one function name is, I remember it starts with he point or something. Okay, just you check. Okay, this there are some functions. Okay, that actually you do not need to give it randomly. It starts with some initial good guess. Okay, that function actually because of the from the training data. Okay, whatever training data you have, so from this training data, this function is actually estimates some good initial values of weights, and that for using that you can start.
Okay, fine, sir. Thank you, sir.
Yes, any other?
Hello, sir.
Two
Am
more
I audible,
questions,
sir?
Yes.
Hello, sir. Am I audible, sir?
Yes, sir. Yes, sir.
Sir, that error function you mentioned, sir, E is equal to 1 divided by 2 sigma target minus O.
Yes, yes.
That function gives you only one minima, that is global minima.
Yes.
Suppose if there is local as well as global minima,
Hmm.
then how that error function looks like, sir?
Okay. This error functions will be same only. The error functions will be same, but we are going to see, okay, in this next part, that how we can overcome this local minima problems. So you'll see that we have this local minima and there is a global minima, right? So if I start, for example, with this W's here, okay, so and then what will happen? It will move like this, and then at some point it will stop. Okay, whatever we have studied, and then that will tell us that this is the minimum. But there are some algorithms like RMS prop, Adam, and momentum. This will actually push the, and then they will say that okay, no, it's not the minimum. There you can check with. So it will push from here and then show you that okay, there are some other parts, and then it will close to come here.
And so that error equation I'm asking, sir, how it looks like if we have both local as well as global minima, sir.
How it visualization?
The error function is a parabolic, it's a squared function, so it always gives you the parabolic curve. If we have both local as well as global, then how that error function looks like, sir? The
visualizations. You want to see visualizations or this error?
No, sir. Equation. I'm asking, sir.
Equation will be same. Global. Equation is same.
Okay.
Equation will be same. Okay, so it's a quadratic because it will be see. It's a quadratic with this different dimension. If you if I'm saying that, for example, when you have this 11 weights W's, okay, so that means if there is a so 11 number of directions for this error surface. This is the error. Okay, so I could visually show you only with this two dimension W1, W2, and this is the error. Now you see for this 11 direction of these W's. Okay, and then you have this error. So if you this errors will be always the same equation. Okay, this is the equation only. We'll be solving this equation.
Yes,
it's a quadratic equation.
So
it is a quadratic equation. We are going to solve this quadratic equation only.
Yes, it's a square now, so it gives parabolic. So if we have both local parabola, global parabola, then how that entire equation looks like, sir, I'm asking, sir.
How this entire equation? How this entire equation actually, this is here you see this in this equation you have D is what? D is the actual output.
Expected output.
No, D is the ground truth. D is the ground
actual output.
And Y is the predicted output.
Predicted output, yeah.
For if you have 100 examples, for let us consider for a single example, one rth example. Okay, so for rth example, so you have this D, this is the ground truth, and what is the Y? Okay, so that's basically you have this prediction. So that's actually the curve is D minus Y whole square. Okay, so sometimes you will see that because we will be doing for each examples. Okay, so at some points when we will be having this surface, okay, so if you change these W's, okay, some points okay, I think I stuck here. I don't know how to visualize these parts. Okay, equations.
It's okay, no problem, sir. It's okay, sir. You can continue.
Okay, so this is just equation of this, just this subtractions and the mean squared error. Okay, so mean squared error it will be, so there will be 3 points where actually this, you actually use this local minima problem. So one is you have this what you say, this shoulder. Okay, so for example, you are going down and then you have some small surface, plane surface, and then after that it's going down. This kind of surface can come. So that means that it is not up, but it is a plane. So here when I'm just going down, so in this point I'm not getting better informations. Means I'm not able to go down. So this is the stop points. This is one case. Second case is this local and global. Okay, so here there will be some local small jitters. Okay, will be there, and there will be some global. Okay, so I can show you this one equation. I have one surface equation. I think that will be better if I show you. So this is another surface. Okay, so where actually you have some points. Okay, locally, this is also another local point, local minima. Okay, here, and then another global minima. These kinds of surface also can come. And this is another surface. Okay, so this is also some surface where we start from some positions and this is the minimum. Okay, so how we actually go down to this minimum. Okay, sir, you please send me a mail maybe if there is something more.
Okay.
So I'll
okay, sir.
Okay, thank
I'll
you.
communicate this, sir.
Yes,
Thank you.
yes. Any other? Okay, so I think we can start. Right?
We can start with the. We can start, and maybe at the end you can take up again.
Yes. We do not have time left. So what we want. So we have this. We have seen this multi-layer perceptrons where we have multiple perceptrons are there, which try to solve this one problem together. And we have seen in this multi-layer perceptrons, we will have many parameters. So how we can train those parameters. Okay, so that means how we can adjust those parameters. So now the question will be that whether we can go to this minimum one or not, and then even if we reach to this minimum, then how long it will take, whether I can do it faster or slower. Okay, will it take means how many epochs it will take. So can we do it maybe in a faster way? Because if you see in this convolution neural network or RNN, CNN, there will be millions of parameters, millions of weights. Okay, so many weights. So if you want to adjust all of them, so it will take lots of time. So that's why we require this GPU. Okay, so with CPU we cannot do all this calculation. So it will take 5 days, 6 days, even with this GPU for getting the minimum solutions. So now the question is how we can make them a little faster. Okay, so when we have so many parameters. Now let us discuss this that overfitting, underfitting, regularizations, and optimizations. So when we have a problem, so we have seen that, for example, XOR problem or this one simple problem like with this, as one of you said, that 4 inputs and 24 examples are there. Okay, and then if you consider, for example, 1 perceptrons only or 2 perceptrons, okay, so then also you get the results. Okay, there if you are using only 2 perceptrons for any of this problem, then what will happen? You have less parameters. Okay, so less parameters means the network, this architecture, multi-layer perceptron architecture is not able to solve. Okay, so I'm not able to find out the weight, okay, values, so that it will give the solution. Means whatever it says, there is actually error. So for training data also you will get error. For testing data also, testing means validation data also you get error. So when the number of parameter is small, so if you have this kinds of data that you have, for example, positive data, negative data, because you are using only two parameters, so you will have only a single line. So with the single line, you actually cannot separate this data properly. So that actually says about underfitting. When you want to solve this problem with, for example, 200 parameters, the same problem, then what will happen if you have 20 parameters means, for example, you can go for 3 layers, in each layer 3 parameters, 3 perceptrons, second layer 10 perceptrons, third layer 5 perceptrons, something. Okay, so that's actually a huge for this problem. So what it will do, it will try to overfit. Overfit means whatever training data you have, from those data, those weights will be so much tuned that for each of this training data, it's actually finding a, it's changing the line. Okay, so it is so much tuned. So this is the hyperplane for the training data. Now, if you use some different data like validation data, okay, in this case, okay, because you have this model now give us some different data. So it is possible that, for example, if the gate data is here, it is a positive data. And now because the surface, the hyperplane is so much tuned, with this data, it cannot give you the predictions. Okay, so it will say that it is cross because it is in this outside of this circle boundary. So because of the so much tuning, it is not performing well. So in this training data, with this number of parameters, when the number of parameters is big, large, then it overfits. So means it's the plane is highly tuned, and validation data you are not getting the results. Okay, the results is poor because that is called overfitting. So we want something in between. Okay, so that it is fitting properly in the training data with some errors. Okay, so we want something like this. Okay, so we give some provision that, okay, so in the training data you also get make some error, but in testing also you do better. So that's more or less in the in between. Okay, so underfitting and overfitting. So that we want. So we do not want underfitting and overfitting. So underfitting happens when a model cannot capture a proper relationship between input and output. The model performs badly on both training and testing data. Means the number of parameters is small, only 1 or 2 parameters, then it cannot actually find out the separator. Okay, so that's the problem. And when this its number of parameters is huge, so it is learning the noise or all the data. Okay, so there will be an issue. So it will not give you the proper results on the testing data or validation data. So if you see this now, if you have the data, so this, if I just find out a simple line, okay, and that's actually underfitting. So underfitting, what will happen? This provides high bias and low variance. High bias means this line, okay, so this, if I'm just considering this is a regression problem, okay, so it's a regression problem, means can I fit a line to these points? So if it's if I'm just using only 1 parameters or 2 parameters, that means this line is actually not learning properly. So given any data, for example, here, some data I'm giving, so maybe it is here, so but the prediction is here. So high bias means, that means this data, this model is not learning anything. Okay, this is called high bias. So given any some data, the model predicts some line which is not at all close to the points, and here you will get low variance because given a new set of data, a different set of data if you provide, there will be also similar error. Okay, so means error will be always same. So when the high bias is there, that means whatever data you provide, always there will be error. If you go for this overfitting, so if I'm using, for example, instead of these 2 parameters, I'm giving 5 or 6 parameters and then I want to fit this line. So for each of these points, there will be a overfit, means it is highly tuned. So there it's actually low bias, means it is fitting to the model, to the data very well. So that is called low bias, means there is no error, okay, in this data. Whatever data, training data is there, there is no problem. But if I am giving another set of data from this data set, so there will be a lot of error. Okay, so for example, if I'm giving some another data testing cases, there will be error. So this will come as high variance. That means in every time the error will be different, more. Okay, but still the bias is low because it's actually fitting. So that's why it is called overfitting, low bias and high variance. Low bias means there's actually, it is fitting the data properly, but if it will provide different variations of results, okay, because if we provide different data sets, if you have for some other data set, there will be a different data. Okay, so that means for every time there will be a different error. So we want something like good fit where you have this low bias and low variance. Means what low bias means, it is actually fitting the data, and variance means, low variance means what if you give a new data points, a set of points, then also variance will be low. So we want something like this. So to do this low bias and low variance, so this is very tricky. Okay, so because if we have less number of parameters, we go for this underfitting. If we have more parameters, we are going for overfitting. So now how can we adjust the number of parameters so that it can give a proper fitting? So if you see that when I am having this in this capacity, that means this is the number of parameters and this is the error. When this number is going less, then I am actually having this underfitting zone. And this parts, when the number of parameters are increasing, then I am going for overfitting. So when I am increasing the number of parameters, then this generalizations is actually affected. Means this model. So if I am having, for example, after 2 parameters, if I'm just increasing the number of parameters, then the training error will be less. Okay, this is a training error will be less. But for testing errors or for this other data, generalization data, the model is not learning properly. Okay, so that means when the number of data is increasing, there will be a gap of the generalizations. So how to do it? So we have 2 things. One is normalizations, norm of this penalties. Another is you have this augmentations. Either you can increase the number of data. So for example, you have 24 data, as you said, that 4 set of features and 24 examples. So can we increase number of data? Okay, so instead of these different experiments, I can increase the number of data. Then that's called data augmentation. And then another case is norm penalties. Okay, so there will be, these are the regularizations. So how we can stop that? Okay, so this weights, whatever weights we have. So for example, if I'm just using 20 weights, W1 to W20. So all these weights will not be fine tuned. Okay, so that was the issue, right? When we use this curve here. Okay, so that means all these weights were fine tuned. So because of that, there was overfitting. So what we want, we do not want all these weights to fine tune. So we will control. We'll put some control that, okay, so after some points, we do not change. This W's will not be modified. So here you have this 2 terms, L1 norm and L2 norms, that we are going to discuss, that they handle in this way, that if weights are large, means if some W's are very large, then they will control. Why? Because if there are W values is, for example, 0.8 and some values W is 0.2. Okay, so W is 0.8 means it's actually a dominating. So if someone is x1 and some another variable is x2 is modified with this W as 0.2 and xy is multiplied with 0.8, if some w's are 0 large, then a small change of this features, okay, so it will be affecting the total results, because I am multiplying x1 into w1, right? So if, for example, x1 is 0.2, then I will be getting some results. If I am adding it, the x1 is 0.9, then the sum is actually, result is affected a lot. Okay, so what I will do, I will try to say that to control this w values, that this w's will not be very large. Okay, so how I can control this w's? So then this should be, all these w's will be uniform. Okay, that we want. That if weights are large, a small change in feature can result in a large change in the prediction. Also, it gives too much influence to some features. So I'm seeing this w 0.8 means, this means in this, for this results, some features are very important and some features are not so important. Okay, so how we can control them? So weight panel, use some control them, and we'll say that, okay, so the weight should be smaller. Then if the weights are smaller, then the model will be simpler and there will be less overfitting. Okay, so when I'm saying this small weight, means this weight values will not be large. That means the equation, this overfitting L and this hyperplane equation will be simpler. Okay, so if I am having a very, some value parameters as 5 parameters, okay, and then some equation, some parameters w1 x1, let us consider this equation w2 x2, okay, something, and then some values are large and some values are low. Okay, so then actually this functions is actually very zigzag. Okay, it's a very complex problem. If it is very simpler, okay, so uniform, then it will make the model simpler. Okay, and then it will make the model with a not very overfitting. So that's actually our target. So we do not encourage large weights. We will go for small weights values in the where we will be adjusting our weights. So that means we have to penalize some weights when they are going to increase. So how we are going to do it? So in that equation of our error, so we consider only this E. So this loss term is basically E in the multi-layer perceptrons. Okay, this is the E, and theta is the weights. Okay, so I've just changed this formula. So here you have this L is E and theta is W. Okay, so initially we considered only this error term. Now what I am saying, that there is also another parameter that's called regularization parameter. What it says, it provides a additional penalty, that theta 1 square, theta 2 square, theta means whatever theta means W1. Okay, so whatever error you have, and then plus, I'm saying this, if I'm just calculating this theta square, that means it will be W1 square plus W2 square plus W3 square. Okay, so this is the error. So it's not only a single error, but it is also controlling this. We are just adding also this square term or L2 terms of all these weights. So this, if some W's are large, that means this error will also be large. This full term will be large. Okay, if this any term W is very large, then this error will be also large. So we want to reduce this full loss. This total loss I want to reduce. That means we have to reduce also this part and this part. Okay, so that's what we want to do. So we will say that this is the penalty term, means if some weights are going larger, we'll control. So here you have this this is the regularizer term. This is another loss. Okay, the regularizer is an additional constant to the cost functions, and it keeps the parameters more normal or uniform. Okay, so there are two kinds of terms. So you see that here we are considering two loss. First, initially in the multi-layer perceptrons, we only considered this part term E, Now we are considering another term, that is with lambda of theta 1 plus theta 2 is something. So there are two regularizer techniques. One is ridge, another is lasso. Ridge is called L2. Okay, so when I am adding this error term, okay, you have seen this actual minus predicted, okay, d minus yk, whatever. Okay, so it's actually opposite. So d minus y square plus lambda of, you have w1 square plus w2 square, all this. Okay, so this term. So this is the ridge. So this full expression I want to minimize. Okay, so I want to minimize this full expressions. That's the error. So it's the error, and it is, this term is added as the penalty. So when we want to reduce, so we want that this w terms will not be very large. So if some w terms are large, then it will error will be also large. Okay, if w is less, then it will be, this error will be less. So it's actually controlled. So it will, if some w's are going larger, so it will stop. As the complexity is increasing, regularization will add the penalty for higher terms. This will decrease the importance given to higher terms. Okay, so higher terms will not be considered. And then you have this another one, that is the L1 normalization, regularization. So this is called lasso. So it is, you just consider this only the terms like W1. Okay, this is the magnitude values. W1 plus W2. Okay, all this. Just whatever weights we have, we just add them. Okay, we just add those magnitudes. Okay, so here it's the L1 regular. So this is the penalty. Okay, so in lasso, it happens that if it may make some of these weights as 0. Okay, so because of these penalties, if some weights are not so important, so it can consider that W can be 0. Okay, so because of this procedure of this penalty terms. So now let us see some visualizations. So if you have this data, of course, that I have explained you in the last day also. So if I am having, for example, if I just use without any regularizer, so this is a using this neural network, and then you see this boundary, hyperplane boundary. That's a overfitting. Okay, overfitting means you see this surface, this plane. Okay, these are very much tuned with this some of the noise. Now if I am using regularizer, okay, so with this L2 regularizer, okay, so and lambda is 0.7, you see this curve here, it is little smooth. Okay, so it's not so overfitting. So L2, L1, this will make sure that this curve is not so fine-tuned. So it will allow some error in the training data, so that in testing time, the results will be better. So that's what about this regularizations. And now let us see this optimizations. Okay, so we have discussed this gradient descent algorithms. So in the gradient descent algorithms, what happens that we use in our multilayer perceptrons, we have, for example, if we have 100 examples, for each examples, one examples, we find out the error and then we modify the weights. Then second example, we find the error and then we modify the weights. Okay, this is possible. This is for each data I can do it. There is another possibility that we can do it for, I can calculate for each example, 100 examples, I find out the error. So I'm not calculating the error. I'm just, I'm finding this for one example error, second examples I'm finding error, up to 100 examples, whatever error. And then I am just taking the average of all these errors and then I am modifying these weights. So this weight modification is done not after every step or after every samples. This weight updation is done after all these examples. Okay, so that's the different way that how will you make it faster or slower. Okay, so if you see that when I go with this with a small for each samples, if I want to modify the weights, it will take long time. Okay, and it will take also lots of iterations to convert. So there are different ways. So first one is the gradient descent. Okay, simple gradient descent is take all examples at once and then you modify the weights. So the weight modification will be done after each iterations. So if you have 100 data, so you find out the error, okay, for one examples, two examples, and then if you have 100 examples, then you calculate the total sum of these errors, okay, for 100 examples, what is there, and then you modify these weights, okay. So weight is the new weight will be the old weight minus eta into that we have seen already. So that actually you have to modify after all the data you cover. That is the gradient descent. If you want to go for stochastic gradient descent, means after every data we modify the data. That we have seen, okay, in our examples. I think we did like that. So after every examples for each weights are modified for after every examples. Now you see this the visualizations of CNN model, convolution neural network models, with this MNIST datasets. Okay, MNIST datasets, you know, this handwritten datasets for 10 classifications, and this loss functions it's actually showing. Okay, so but it is the stochastic gradient descent. Okay, stochastic gradient descent is the for after every samples these weights are updated, and it is actually it was done in our lab, and this is the visualization. And you see this error is actually very going down very slowly. Okay, so this iterations, so this process is very slow. Okay, so we have this error, it is the loss functions. Initially there will be a huge loss, and after some points, after some iterations, there's actually loss is going down. Okay, so and we have used it in the CNN model. It will take a lot of time. Okay, so I just skip it. And then we have this mini batch stochastic. So what we do, we have mini batch means instead of this single gradient descent, okay, single data stochastic gradient descent models, which is actually very slow. And if we are using this full data, all the data examples, then what will happen if we take all the data? So there will be very zigzag. Okay, so sometimes weight will be 0.5. The second time, next time you see this W will be 0.65, and the next time it will be 0.4. Okay, so because why it's changing up and down? Because some in this training data, some examples will be giving positive error, some examples will be giving negative error for the same value. So you will have some issues with this setting this W. So there will be a zigzag, but it will give you the convergence faster than the stochastic gradient descent. Okay, so it will be faster than the stochastic gradient descent, and but the problem is it may skip this minimum problem. Okay, this weight minimum problem, because there can be several zigzags. Because you are going for 100 examples, all these examples, some will giving you positive error, some will give you negative error, and then finally at the end you are just making assumptions. So you do not know whether these weights are you need to add or some weights are needed to be decreased. So if this total value is decreased, then you change those weights, but you see at the end you are not converging, you are diverging. Okay, it's possible. So there will be lots of zigzag. So to avoid these two key things, either this in the stochastic gradient descent and the simple gradient descent, we go in the middle path, that's the mini batch. Okay, so mini batch, what it does, that I can consider, for example, 2 samples together or 4 samples, means for example, instead of this every samples, I consider 2 examples, and this 2 examples I see whatever errors is there, and after that I modify the weights. That is possible that after 4 examples, I can consider also after 8 examples. So there are actually different batch size. Then you will learn about this batch size. 2, 4, 8, 16, 32. Okay, so usually it's a power of 2. Sometimes 64 also. So batch size of 64. That means batch size of 64 means in the weights are updated every after 64 examples. Okay, so 64 examples are taken, and then we can get the error, and then we find out this what is the average error, and accordingly these errors are updated. So this is the rule. So we have already seen this. For example, it is if it's 64, so 1 by 64, and then we just calculate the 64 samples data and error, and then we modify the weights. So when beta, this number is 1, that means it is coming as this stochastic gradient descent only. So here you see this mini batch gradient descents. Okay, so that's actually faster. Okay, for this convergence, and you have seen this stochastic gradient descent. It is very slow, and this mini batch gradient descent is faster. Okay, than this stochastic gradient descent. Here you see this depending on this error. Okay, so someone, if you ask this error surface, okay, so you have seen this some curves are there, right? Okay, so that's actually the stochastic gradient, mini batch stochastic gradient, and then gradient descents. Now let us see this some other algorithms, how we can make it this faster. Okay, this gradient descents. So it is possible that in some cases this weights are stuck in this local problem that I was saying, that there is some local minima and it is stuck. Then how we can get rid of this local minima? It is we can use some momentum. Okay, so this is a, there are actually different other optimization techniques. So some of them these are momentum, Adam, RMS props. Okay, so momentum, what it does, that's actually it is something like whatever we have this history. So this, from this knowledge of history, I will use that history, and then even if I stuck, then I will push that. Okay, so that uses this, that uses the history of the previous gradient informations. So that's the momentum. So it is like analogous to rolling a ball with a mass and gravity on the topology of the objective function. So let us know, if you have this error surface here, and then you are rolling a big ball, so with a mass. So what will happen? Even if it's stuck, it will go there, and then it will start continuing. Okay, that's the idea. So how we actually do it? So means we need to store the gradient of the previous cases. So after first iteration, what was the gradient? After second iteration, what was the gradient? So we need to remember them, and we need to store them. Okay, and then we will be accumulating, and whenever we start at the next step, the current step, we have to add that previous information as well. Okay, previous gradient information we need to add to know that whether it should stop or it should go. How? So this is actually a simple formula. Okay, so that's momentum. So the updation of this gradient is based on the moving average. Okay, so what it is doing? So we have seen this gradient information, that the simple gradient information, whatever we have learned. Okay, it's actually this regularizations, including the regularization L1 or L2 norm. Okay, so it is, you have E plus some lambda of, it can be W or it can be W2, whatever. Okay, so it's L1 normal. It's the, this is the total gradient loss functions, and then
It seems he is disconnected. Hello?
Ma'am, sir is here in the meeting.
Okay. I thought that I was not getting his voice. So I got
Yes, ma'am, voice we are not getting, but his name is there in the list.
Yeah, I can see his slide.
Madam,
also.
is it okay? Shall I
Yeah, your
continue?
voice was muted, in fact. Yeah.
My voice was muted?
Yeah. Just now. I mean, a couple of minutes, just a minute ago.
Oh, is it okay now?
Okay, I can see your slides and your voice also, we can hear.
Okay, fine. So what? Okay, so if what the part I missed, I don't remember. Okay, so I'll discuss. I'll continue, and then if someone is having problem, we'll discuss. So we have seen this is the gradient. Okay, gradient is in this. You have this error surface. Okay, error functions, and we are using this gradient. Okay, that's the gradient. And now, as I said, that we have to use the history of this gradient informations. Okay, so this V is storing the history information. How? It says that whatever you have the previous timestamp, whatever it was gradient, that you keep for 90%. Okay, so for example, in the first step, I am having a gradient of 0.5. So in the second time, what will be happening? So my gradient will be alpha, means alpha is 0.9, because 0.9 into, okay, the previous gradient 0.5 plus eta. Okay, so eta into means some number, eta is, for example, some numbers consider 0.5 into gt. Okay, so this is the next step. Okay, this is the current step. So it was the old previously. Okay, so let me repeat again what I said. So initially, let us consider that I am starting now. Okay, so this gt is 0.5. Then you do not, and this dt will be, you do not have the previous value, so it will be eta into 0.5. Then theta t will be whatever you have the previous value. Okay, so it was the, let us consider this is the this first time, and this will be bt. Okay, the whatever value you can calculate. Second time, in the second step, gt, if you will consider the second time, the gradient is 0.7. Then we are storing we are using this now, the previous one. So Vt will be momentum, what we are doing, alpha into Vt minus 1. Alpha means it will be 0.9 into Vt minus 1. Vt minus 1 means this value. It will be eta into 0.5. And then plus eta into gradient 0.5. Okay. And then what will happen? No, sorry, this is gt. It will be 0.7. This is the current value. So you see that in this momentum, we have used the previous value. Okay, this previous value, eta into 0.5 plus this next value. And this previous value is given more weightage, 90%. Now, if you are going for this next step, so those previous values are given more weightage. Okay, so that's the momentum. Okay, so we are keeping up storing this previous gradient informations, and those gradient informations are used for finding the change of this current weight values, whether it will be increased or decreased. So it will not depend only on the current gradient. It will depend on the current momentum, not the gradient. It will depend on the current momentum. Okay, so that's the momentum. If you have this curve, and if we use this momentum, you will see that this loss will be, I will show this all these curves together at the end. This momentum will be better than this stochastic gradient descent or gradient descent. Then we have this RMS prop and then Adam. Okay, so RMS prop also uses this, instead of this simple gradient, it uses the squared gradient. Okay? So it uses the square, but it is also using this previous informations. Okay, the RMS prob, momentum, they are all same. They are not using only the current gradient, but the previous histories of the gradients. So here they are using squared gradients only for finding the latest value. And in RMS and ADAM, they are using square term and gradient. This both terms. This is a combination of ADAM is combination of both momentum and RMS probe. Okay, so that's you have this. ADAM is actually faster. So usually in our CNN or this deep learning algorithms, we use this ADAM optimizer. Okay, so because of this faster process. And there are also some other algorithms like ADA delta, ADA grade, energy. Okay, so here you see this which one is faster. So if all this algorithm starts from the same point, okay, and then this red one is stochastic gradient descent. It's actually going very slowly. You see this this black one is RMS probe. It is very fast. And you have this blue one, yellow ADA delta. These are also faster. Okay, so you see that how this is the local minimum. So how we can go from this initial points, initial configurations to this minimum points. Okay, so here also this is the similar. So for example, it's the saddle point. Okay, so where it is some a minimum as well. Okay, but if you go in this other directions, then it will go to the global minimum. So here you also see this ADA delta is faster. So now in this visualization, you see a comparisons of all these algorithms: SGD, mini batch, SGD, momentum, ADAM, RMS probe. So which one actually gives you the minimum error? Okay, faster. Here you see this ADAM or this RMS probes, these are more or less close, whereas SGD is very slow in this reaching the minimum surface. Okay, so that's it. I think I have also come close to this time. So thank you. These are some organization I am getting support. Thank you. So yeah, you may always drop me mails in this polymal.iit.ac.in. You can go through my work and send me mails at this cs.iit.ac.in. Thank you very much. Yes.
Thank you so much, Dr. Path Ray. And
thank you, madam.
It is, as I always say, it is always a pleasure listening to you. There are a couple of hands which have been raised. Would you like to answer?
Yes, sure.
So the first one is some Satya. I'm requesting you to unmute yourself, please. Yeah.
Good afternoon.
Yes, sir.
Sir, my question is, can we decide the number of hidden layers in the neural network?
No, this is a hyperparameter that you have to try with this different.
How we will take to the number of hidden layers?
So you can try with this. So depending on this complexity of the problem. Okay, so how many input features are there? If you have a small number of input features, I think you can go for according to this ratio. Okay, so for example, you have 2 times maybe square root of this number of features. Okay, so that kind of number of layers you can go, but number of neurons you can take. But usually, if you are going for multi-layer perceptron, simple multi-layer perceptron that I showed, that 2 hidden layers are sufficient to get the approximate results. Okay, so
it's not depend on the number of neurons.
Number of neurons, of course, because see that yes, number of neurons, it's up to you have to try with this different combination, because you have 2 layers are sufficient. Now in each layer, how many neurons you will put, that is, so if you increase the number of neurons, that means you are increasing the number of parameters. There will be a chance of overfitting. Okay.
Thank
So if you have less number of neurons, that means there will be underfitting. So that you have to see that, okay, so whether you want to go for high number of parameters or low number. If you go for high number of parameters, no issue. You just use this regularizer. Okay, that's enough. That's
okay. Thank you, sir. Thank you very much.
Yes. Yes, any other questions, madam?
Amit Kumar Pandey, would you like to please unmute yourself and ask question?
Yes, sir. My question is regarding this regularization again. So in which scenario we should go for L1 and then in which scenario we should go for L2? What I understand from this class is regularization is again to fit the model, to go for a good fit state. But
so usually people will prefer for this L1 norm. Okay, so L1 norm will you can take, and then L1 norm is actually preferred because it will penalize some of these weights, and then this will make some zeros. Okay, some of these weights will be zeros. Okay, so there you can get some of this. There will be no overfitting. Okay, that's much. Oh, but L1, L2 both are okay. Sometimes both are combined also. In some cases. Okay, but usually you can try both. But if you do not have any choice and you want to do it with a single shot, then you can go for L1. But in L1 also you have to see this one parameter things are there, that is the lambda. Okay, whether you will go for the high values or low values. If you are going for low values, okay, so means if it is 0, lambda is 0, that means this part is 0. So that means this you are not using any regularizer. If this lambda is very small, that means this penalty part is very small. If you are going for high value, that means then you will have more or less you are penalizing some of these parameters. Then some of this weight maybe come to 0. It's possible. Okay, that means you are penalizing some of these weights which are not required. So there, in this case, you actually reducing the number of dimensions. Okay, so some of the features which are not useful, those weights will be come to 0. Okay, if you are using this L1. Okay. If you so L1 norm is better. Yeah, in many applications, L1 is shows better results.
Yes. Shall we go to the next? Yeah, Darshan LM. Please unmute yourself. Yeah.
Hello, madam. I'm audible, sir.
Yes, sir.
Sir, can you differentiate what is the difference between bias and variance, sir?
Okay, so bias and variance is. So bias is, for example, if I am having a model, if I am having some data, okay, so if I am having a data, and then bias is if I make a model, okay, so if I make a model, and this model is this one, or another model this one, okay, this model is doesn't fit at all here, okay, this is a high bias, and this is a low bias, okay. So this model doesn't fit at all. This is for any data set, this will not give you results. When I'm saying this variance, okay, so variance means when you have, for example, a model here, and then this model is very high tuned, okay, very high tuned. So what will happen? For some data, it will provide you some results. It will give you good results for some data sets. D1, it will give you, the accuracy is very good. For example, the accuracy is 100%. But if you have another data set, means some part, for example, validation data or another part, then you will get lots of error. Okay, so maybe the error will be 40%, so you will get 60%. So that's actually, you will have lots of variance. Okay, so for different part of the data, you will have different kind of for some kind of data, you will not get results. This is the variance. So if your model is very overfitting, then your variance will be high. Is it okay?
Okay, sir. In the yesterday class, sir, you said bias is equal to 1 in the yesterday.
Oh,
class.
that bias and this bias is different. That is actually, yeah, this what I will say, this is the problem in this literature, that these are the same terms they have used, but that bias is actually whatever we use in this neural network, that y is this summation of wx, okay, wx plus b. Okay, so this is actually the intercept. Okay, so if you have two features, and this is the line, and this b is basically the intercept, and this is called also bias. Okay, and in this problem in machine learning, when we fit the model in this data, there you have these two terms. This bias is totally different than this this bias. Okay, sorry for the confusion, but it is actually in the literature they term it like that. Is it okay, sir?
Okay, okay, sir. If you are free, can I ask you now?
Yeah, please. English itself has a lot of so many common words used for different context, for with different meaning. So that is a problem. Please continue.
Hello, sir.
Yes, sir.
So, what is the? I'm asking last question, sir. What is the impact of underfitting, sir? After because I trained around 5,000 images using this neural network. What is the impact of underfitting, sir? After training around some images and all, how the network going to behave once the model become underfits?
Underfitting means this model didn't learn anything from the data. So when I say that you have, for example, the data, okay, something like this, you have some positive data, these are the negative data, okay? And see, if you have only two neurons, okay, two perceptrons, and you make a simple line, simple separator, okay? So this actually is not a good separator for these kinds of problems. So for example, given any new data comes, okay, so for example, if the data comes here, across, okay, so this will be considered as positive circular. Okay, so underfitting, it will not provide results, good results in the training data as well as testing data. Okay, so underfitting will not provide results in the training and testing. What does it mean underfitting? Means when the number of parameters are less. Number of parameters means when you have less number of perceptrons. If you increase the number of perceptrons, then there is a chance of overfitting. Overfitting means it will be highly tuned with the data. So if there are some noise, for that noise also it will be tuned. So for example, if this is noise, you have another noise here. Okay, but so for this it is a noise, it should be cross, but it was considered as a circle, okay, because of noise or outlier. So this model, this overfitting model, what it will do, it will try to fit also this point, something like this. So this will cause the problem. Because if even in testing data, there is a possibility that many cross are coming in this way, this will be all considered as positive. Because of this highly tuned, this separator. If this noise was not there, then it was okay. Okay, so that's why we need to have a model which is not so overfitting or which is not so underfitting. We need something like this, which will allow some error in the training.
Okay.
Is it okay?
Fine, sir.
So if you get underfitting, that means you need to increase the number of perceptrons, neurons in your model. Either with increase the layers or increase the number of neurons in each layer, and then it will be proper fitting. It will not go to underfitting. Yes. Next question.
Yeah, this is the last question, and then I'm requesting Satya Devi to please unmute herself. Satya Devi.
Yeah, good afternoon, sir.
Yes, madam.
Yeah, sir, what is hyperparameter?
Okay, so hyperparameter means, see, you have, for example, these are the parameters, that number of what is the number of weights? Okay, this
Whether it is relevant to the architecture, that is the topology, or else with this, that means
yes,
that
yes. When I am saying this hyperparameter, that means these are the topology. That's number of layers, number of nodes in each layer, or then what is the activation functions, or for example, this eta. Okay, so eta value of learning rate, or some parameters are there which are actually not directly affecting, but indirectly they are affecting. Okay, so these are called hyperparameters.
Then for this regularization parameter, this is relevant to this.
Yes, regularization parameter, this lambda, this is also a parameter. Yes, this is also a.
This is also a hyperparameter.
Right, yes.
Okay. Oh, okay, sir. Okay, thank you.
So at the end, once again, thank you, Professor Partha Pratim Roy, for your wonderful 2 sessions. These were so comprehensive session with each and every detail. With meticulous care, you have prepared all the slides. We are so thankful to you. You have always been helping.
Yeah, thank you, madam. Thank you.
So on behalf of your own academy, IIT Roorkee, NIT Patna, NIT Warangal, MNIT Jaipur and IIIT Jabalpur, I sincerely thank you on behalf of all the coordinators. And we hope that in future as well, we'll be getting your continued support.
Sure, thank you, madam.
With this, yeah.
And thank you all participants for the patience and attending this 2 lectures. Yeah, I know some parts are a little intensive, but yeah, so with practice and if you go through this exercise a few times, then you will learn all the details. But you have to do this yourselves. Okay, that's the key.
Yeah, in 4 hours you have covered so much, but you have made it so clear and crystal clear that I think that this gives them the seed point for learning more on neural network. So with this, I once again thank you and thank all the participants also for their very active participation, asking questions that keeps, especially in the digital era, when we are not able to see the faces of participants, your active involvement makes the sessions so live. We will be meeting at 6 p.m. Purnima Singh Thakur, my student, will be taking up a lab session. She will be covering 2 important machine learning models, methods. One is SVM and the other one is this neural network. She will try her best to also apply for regression problem. But our main idea is to help you understand how these could be applied for classification problem, right? So Purnima will be there to continue with our lab session. Thank you all. Please relax and enjoy your tea, coffee with your family and friends. We'll be meeting at 6 p.m. sharp. Thank you.
Thank you very much, man. Thank you.
Thank you, Dr. Partha. Thank you so very much.
Recording stopped.